Okay. All right. Okay. Now it works. Okay, so the paper addresses the marriage of SQL and UDFs, which it seems that it is not a very happy one. So if we do a Google search about UDFs, we will find various articles and blog posts that do not say so nice things about them. But what are the reasons that UDFs have gained such a bad reputation? At least some of the reasons is that first of all, are invoked in an iterative fashion. So when we have a query that involves a UDF, this UDF will be invoked for every tuple that the query touches. And also, the code of the UDF has unknown semantics for the query optimizer, so it cannot be optimized in the same way as a SQL query is being optimized. Furthermore, each statement inside a UDF is interpreted, so the entire code is not being compiled and optimized using typical compiler optimizations. And finally, the levels of parallelism are limited in comparison to what we see in query plans. So really, what we are facing is an impedance mismatch between the declarative nature of SQL and the imperative paradigm that is being used inside UDFs with languages like procedural SQL. For example, in this paper, we will see some examples with T-SQL, which is used in the Microsoft server, but there's other languages like Java or C++ that are being used for UDF development. And another thing, SQL queries are evaluated in a set-oriented manner and not per tuple, like we said for UDFs. So essentially what happens is that we have a lot of context switching between this set-oriented and per tuple-oriented evaluation. And things can get a bit worse when we have UDFs that inside their code, they execute SQL queries. So again, we go from the per tuple evaluation to the center-oriented evaluation and back. But the solution is not to entirely on UDFs because they encourage modularity and code reuse. So users like them for these advantages. And also there are computations that are easier to express in imperative languages. And they are more readable and easily maintained that way instead of writing the same computation using a complex query where the result might be, of course, equivalent, but the intent will be hidden below this complex query. So the intuition behind the framework that the paper discusses, Froid, is that if we have a query that involves a subquery like this one here, for example, where we want to find the suppliers that offer a specific part with the minimum cost, at the minimum cost. So in this query, the subquery will be evaluated for every tuple that the outer query touches. So here we have kind of the same thing with UDFs. We have again per tuple evaluation. But the good thing is that the community has done a lot of work for optimizing queries with subqueries. So the intuition behind Froid is what if we can transform UDFs to relational expressions so that we can then go and substitute UDFs with subqueries and leverage all these optimization techniques that are already there. Now, in a nutshell, Froid performs the following steps. So when we have a SQL query with a UDF call, the query, of course, is being parsed, and during binding, when the UDF operator is encountered, Froid takes the code of the UDF, it parses it, and constructs a number of regions. So these regions are essentially blocks typical blocks that a compiler is dividing a program to, so it's not something new. And then each of these regions is being translated to relational expression. So finally, all these expressions are combined using the apply operator, which we will see in a bit what exactly it is doing. And then when we have generated this relational expression, the UDF call is substituted by this expression, and the query execution follows then the typical steps of query optimization and etc. So essentially, Froid is not does not require any changes on the database engine, like the steps take place before the query optimization. So it's easy to integrate with existing database systems. Now, let's say that we have the following example. We have a scalar UDF, and Froid focuses on scalar UDFs. It does not describe any ideas for table-valued functions. So everything we will see in this presentation is about scalar UDFs. So let's say that we have this function, the total price, which takes as input the key of a customer. And then at the beginning, there are some variable declarations and variable assignments, some of which also need a SQL query to be performed. And so initially, we want to compute the price for all the orders that have been made by this customer. And then we want to find his preferred currency. So if his preferred currency is different from the default currency, then we want to compute the exchange rate, which is also being computed using another UDF down here. And then we multiply the rate with the price of the orders and return a string which consists of the price and the preferred currency. So we can see that the code of this UDF is being divided into regions. For example, we have in the beginning a sequential region, and then we have a conditional block here. So what Froid does is that it translates each of these statements to relational expressions. For example, if we have a variable declaration, we can use a projection to represent it. Let's say here we have the default currency variable, which takes as value the string USD. So we use a projection to represent this declaration. If we have a declaration without assignment for a variable, we do the same, but we use null as the value that is being projected. And we can also do the same for variables that are that take their value from a SQL query. Now, for a conditional statement, in order to represent it, we can use a case when statement in SQL. And finally, for a return statement, what happens here is that an implicit variable named return val is being projected, and then there needs to be an unconditional jump to the end of the statement when we have, to the end of the function when we have a return statement. So in order to implement this mechanism, Froid uses the probe and pass-through functionality of the apply operator. So probe, it checks whether the return val has been assigned a value, and pass-through ensures that the rest of the statements will be executed only if there is no assignment to the return variable. So in total, the statements that can be supported by Froid currently are, as we saw, any variable declaration and assignment, conditional statements, and return statements. So these are all the supported constructs. So now that we have we have translated the statements, we can combine these statements into regions. And to do so, Froid uses derived tables. The schema of these derived tables is determined by the right sets of the region. So each region has a set of variables that reads and writes. And for the derived tables, we are interested in the right set of the region, the variables that are being written. So for example, for region R1, we have 4 variables in the right set. Those are the price, rate, default currency, and pref currency. And excuse me, and those are essentially the attributes of the schema of DT1 of this first derived table that are being projected so that they can be referenced by derived tables, by subsequent derived tables. For example, we can see that the table DT2 is referencing variables from the derived table DT1. And we can see here that these derived tables are combined using the outer apply operator. So what does this operator do? The apply operator takes as input a relation and an expression, and for every row inside the relation, it evaluates this expression and emits tuples that are adjoined between the row R and the result of the expression on R. So essentially, each of these derived tables is an expression that is being applied on a row. So for example, in order to take the final relational expression here, first of all, apply is being, the apply operator is being executed on the derived tables dt and dt2, and then the result that is being generated from this first apply operator is then combined with another apply operator with the derived table dt3. So if we check this example, essentially each of these derived tables is going to emit a single tuple. So we join all these single tuples that are being generated by the individual derived tables. Now then, we end up with a single relational expression. And there is work that can transform relational expressions that use the apply operator into joins. So this work has already been done for subqueries. It's not something novel that the paper presents. It just uses this idea. So since we end up with a relational expression, for example, the query optimizer can infer in our example that we can compute the total price for all the orders per customer using a group by operator, and then we can join the customers table with these computed total prices. So essentially we can replace the apply operators with joins, and the query optimizer can optimize these joins as it usually does. Now, the paper also addresses another question, another issue. Since we have imperative code inside the UDF, we could apply on it some compiler optimization, some typical compiler optimizations. And the authors show how these optimizations can still be applied on the generated relational expressions, so that this potential is not lost. They are describing the following compiler optimizations: dynamic slicing, constant folding and propagation, and dead code elimination. And we have the following example, a very simple function which takes as input an integer and checks whether this integer is larger than 1000. And if it is, then another variable takes the value high, or if it is not, it takes the value low, and the function returns a string consisting of this value plus another string. So above the horizontal line, we have the transformations of the code if we apply each of these three compiler optimizations. And below the line, we have the output of Froid, the relational expression, the generated relational expression, and how this relational expression changes if we apply again these compiler optimizations. So, for example, for dynamic slicing, if we have, for a particular execution, if we have a value that is above 1000, then we can infer, the compiler can infer that the else part of the conditional statement is not going to be evaluated. So it can discard this part of the code and just keep the variable assignment with the high string and the return statement. Now, when constant propagation and folding is applied, so constant folding is when constants can be evaluated during compilation time, and propagation when we propagate their value to every occurrence of the variable that exists in the code. So, for example, here we can, the compiler can substitute the occurrence of the val variable in the return statement with just with high, with the string high. And finally, dead code elimination has to do with parts of the code that are never reached, or for example, variables that are being declared and are never used again by the code. So here, since we have substituted the val variable in the return statement, we can discard the assignment above it and just output the return statement. Now, if we check below the line, we will see that the same optimizations can be applied on the relational expression. So, for example, for dynamic slicing, we see that the case when statement has been discarded, and we only keep the statement that exists after then. And also, we can apply constant propagation as well. We can go and substitute high to the reference of dt1 val var attribute in the second select statement. And if we do this, we can discard the outer apply operator. And finally, we can just project high value without creating any other attribute. So what they want to showcase here is that there is no optimization potential lost, that the same techniques can be applied on the relational expression. Now, there are some experiments, of course, in the paper. The experiments have been conducted on 2 real customer workloads and also on the TPCH dataset. For the customer workloads, the UDFs are being used as they are, and also no workload-specific techniques are used. So the first experiment has to do with the applicability of Froid, and we can see that Froid achieves quite high coverage. So for workload W1, it can translate 85% of the UDFs. And for W2, it can translate 92.5%. And for the UDFs that could not be translated, that was because there were constructs that are not currently supported by Froid. There are also some other statistics regarding the size of the UDFs, the lines of code. So we can see that on average, the UDFs consist of 20-something lines, and the maximum size that they tried regarding these 2 workloads is a bit more than 100 lines of code. Now we can see some time experiments. For the first plot here, a simple query is being used. We have a simple select query that just projects the result of a UDF function. And the y-axis of the plot is the cardinality of the table. So basically this shows how many times the UDF will be invoked. And the y-axis is execution time. Here, no compilation time is by Froid is being considered on this table. So the green line is the execution without Froid, and the blue dotted line is with Froid, but the degree of parallelism is set to 1. And also the orange dashed line is with, again with Froid, but we have a quite larger degree of parallelism set to 12. So we can see from this plot that Froid achieves 2 to 3 orders of magnitude better execution time. And there is an improvement even for very small numbers of tuples, as we can see here. Now, There is also another experiment that measures the compilation plus the execution time for 15 UDFs from workload W2. So here, compilation time is taken into account in this experiment. And yeah, we can see that with Froid, which is the orange bars, we gain a lot, even though the compilation time is being added up. Now, there are also some other experiments that concern the entire set of UDFs in workload W1 and workload W2. So in these plots, we can see the factor of improvement when Froid is being used. So, and it is being displayed in a descending order, so the higher the better. And what we can observe here is that there are some UDFs that have zero improvement when Froid is being used, or even let's say a negative factor of improvement. So according to the authors, these UDFs were quite complex. They were either containing many lines of code, or they were containing many calls to other UDF functions. So they ended up being translated into quite complex relational expressions that were not handled that well by the query optimizer. And there is also an experiment on the TPCH dataset. So they took some of the queries, and they rewritten part of these queries as using UDFs. And so, for example, we can see the results for some of these queries here. We have the green bar, which is the original query, the bar with the blue lines, which is the query with the UDF but without Froid, and the orange bar that is when Froid is being used. Here we can see that Froid achieves a performance that is quite close to the original query. So this experiment showcases that Froid can achieve a quite decent translation of the UDF to relational expression from a performance point of view, time performance point of view. And now there is also another experiment with Froid on row and column stores, again on the TPCH database, and they use this very simple UDF discount price with this query to do this experiment. So we can see here that already using a column store achieves a better execution time for this particular query, at least. And we can also see that with Froid can achieve quite a lot of benefits both in a row store and in a column store database. And finally, there's also this plot that has to do with resource consumption. And again, here we see 15 UDFs from workload W2 with and without Froid. And the y-axis here refers to CPU time. And again, it's again in log scale, so we can see that Froid can decrease the CPU time by 2 to 3 orders of magnitude. So yeah, that was Froid. It's an extensible and language agnostic optimization framework. And that is because even though the paper addresses T-SQL, it can also be extended to other languages. What is needed is a parser of the language and the definition of the supported constructs for a particular language. Otherwise, the rest of the ideas and implementation stays the same. So with Froid, we can translate UDFs to relational expressions, which can be evaluated in a set-oriented methods that come with this evaluation. And also another, let's say, side effect of this technique is that since the generated result is a relational expression, then this can be executed on relational systems that do not support UDFs. That's a byproduct of the framework. So yeah, that's it from me. Thanks a lot for your attention.
Thanks.
Well, we can clap here.